4.3 Measuring enthalpy changes. The general name for the enthalpy change for any reaction is the standard molar enthalpy change of reaction delta H. It is measured in kilojoules per mole, kJ, mole to the power of -1. You write a balance symbol equation for the reaction and then find the heat change for the quantities in moles given by this equation. For example, delta H for 2NaOH plus H2SO4 equals Na2SO4 plus 2H2O is the enthalpy change when 2 moles of NaOH react with 1 mole of H2SO4. Some commonly used enthalpy changes are given names. For example, the enthalpy change of formation, delta FH, and the enthalpy change of combustion, delta CH. Both of these quantities are useful when calculating enthalpy changes for reactions. In addition, delta CHs are relatively easy to measure for compounds that burn readily in oxygen. Their formal definitions are as follows. So, the standard molar enthalpy of formation, delta FH, is the enthalpy change when 1 mole of substance is formed from its constituent elements under standard conditions, all reactants and products being in their standard state. The standard molar enthalpy of combustion, delta CH, is the enthalpy change when 1 mole of substance is completely burned in oxygen under standard conditions, all reactants and products again being in their standard state. Temperature is related to the average kinetic energy of the particles of a system. As the particles move faster, their average kinetic energy increases and the temperature goes up. But it does not matter how many particles are there. Temperature is independent of the number present. Temperature is measured with a thermometer. Heat, on the other hand, is a measure of the total energy of all the particles present in a given amount of substance. It does depend on how much of the substance is present. The energy of every particle is included, so a bath of lukewarm water has much more heat than a red-hot nail because there are so many more particles in it. Heat always flows from higher to lower temperatures. So heat will flow from the nail into the bath water, even though the water has much more heat than the nail. The enthalpy change of a reaction is the heat given out or taken in as the reaction proceeds. There is no instrument that measures heat directly. To measure the enthalpy change, you arrange for the heat to be transferred into a particular mass of a substance, often water. Then you need to know 3 things: mass of the substance that is being heated up or cooled down, temperature change, and specific heat capacity of the substance. The specific heat capacity, C, is the amount of heat needed to raise the temperature of 1 gram of substance by 1 Kelvin. Its units are joules per gram per Kelvin, or Jg to the power of -1, K to the power of -1. For example, the specific heat capacity of water is 4.18 joules per gram per Kelvin. This means that it takes 4.18 joules to raise the temperature of 1 gram of water by 1 Kelvin. This is often rounded up to 4.2. So, in that case, enthalpy change equals mass of substance times specific heat capacity times temperature change. You can use the device in figure 1 to find the approximate enthalpy change when a fuel burns. You burn the fuel to heat a known mass of water and then measure the temperature rise of the water. You assume that all the heat from the fuel goes into the water. The apparatus used is called a calorimeter, from the Latin calor, meaning heat. The simple calorimeter can be used to compare the delta CH values of series of similar compounds because the errors will be similar for every experiment. However, you can improve the results by cutting down the heat loss. The flame calorimeter shown in figure 3, is an improved version of the simple calorimeters used for measuring enthalpy changes of combustion. It incorporates the following features that are designed to reduce heat loss even further. The spiral chimney is made of copper, the flame is enclosed, and the fuel burns in pure oxygen rather than air. It is relatively easy to measure heat changes for reactions that take place in solution. The heat is generated in the solution themselves and only has to be kept in the calorimeter. Expanded polystyrene beakers are often used for the calorimeters. These are good insulators. This reduces heat loss through their sides, and they have a lot of heat capacity, so they absorb very little heat. The specific heat capacity of dilute solutions is usually taken to be the same as water. Neutralization reactions in solutions are exothermic. They give out heat. When an acid is neutralized by an alkali, the equation is acid plus alkali equals salt plus water. To find an enthalpy change for a reaction, you use the quantities in moles given by the balanced equation. For example, to find the molar enthalpy change of a reaction for the neutralization of hydrochloric acid by sodium hydroxide, the heat given out by the quantities in the equation needs to be found. HCl plus NaOH equals NaCl plus H2O. A metal that is more reactive than another will displace the less reactive one from a compound. If the compound will dissolve in water, this reaction can be investigated using a polystyrene beaker as before. For example, zinc will displace copper from a solution of copper sulfate. The reaction is exothermic. Zn plus CuSO4 equals ZnSO4 plus Cu. From the equation, 1 mole of zinc reacts with 1 mole of copper sulfate. Although expanded polystyrene cups are good insulators, some heat will still be lost from the sides and top, leading to low values for enthalpy changes measured by this method. This can be allowed for by plotting a cooling curve. As an example, the measurement of the heat of neutralization of hydrochloric acid and sodium hydroxide is repeated using a cooling curve. Before the experiment, all the apparatus and both solutions are left to stand in the laboratory for some time. This ensures that they all reach the same temperature, that of the laboratory itself. Then proceed as follows. Place 50 centimeters cubed of 1 mole per decimeter hydrochloric acid in one polystyrene cup, and 50 centimeters cubed of 1 mole per decimeter sodium hydroxide solution in another. Using a thermometer that reads to 0.1 degree Kelvin, take the temperature of each solution every 30 seconds for 4 minutes to confirm that both solutions remain at the same temperature, that of the laboratory. A line of best fit is drawn through these points. It is likely there will be small variations around the line of best fit, indicating random errors. Thirdly, now pour one solution into the other and stir, continuing to record the temperature every 30 seconds for another 6 minutes. The experiment can also be done using an electronic temperature sensor and data logging software to plot the graph directly. On mixing, the temperature rises rapidly as the reaction gives out heat, and then drops slowly and regularly as heat is lost from the polystyrene cup. To find the best estimate of the temperature immediately after mixing, you draw the best straight line through the graph points after mixing and extrapolate back to the time of mixing. This gives a temperature rise of 6.9 Kelvin. The calculation is as before. Energy equals m times c times delta T, which is 100 times 4.2 times 6.9, which is equal to 2,898 joules. The number of moles of acid and alkali was 0.05 mole, as before. So 1 mole would give 2,898 divided by 0.05 joules, which is equal to 57,000 960 joules, or 57.96 kilojoules. So the enthalpy change of neutralization is equal to minus 58 kilojoules per mole. The sign of the delta H is negative because heat is given out.